Hey everyone, and welcome. Today we are going to talk about something that can totally change how you solve problems. It's called computational thinking, and here's the cool part. You don't need to know a single line of code to use it. It's a mental toolkit, and it is powerful. So you've probably heard the phrase, think like a computer. But what does that actually mean? I promise it's not about being some kind of math genius or a coding whiz. It's really about having a structured, kind of brilliant way of looking at any challenge that comes your way. At its heart, computational thinking is really just the art of finding patterns and clear, repeatable steps to get to a solution. Think of it like a perfect recipe. You have a problem, which is your ingredients, and a solution, the final dish. This recipe is the reliable procedure that you, or a computer, can follow to get it right every single time. Now, to really get a feel for this, we're going to break it all down with a really simple, hands-on analogy. Seriously, you can picture it right now. No screens, no code, just a physical process. Okay, so imagine you're holding a physical stack of cards. For real, just picture it. Each card has a piece of data on it. Maybe it's a student's final grade or a customer shopping list. Our whole goal here is to answer questions by just sorting through this stack by hand. This one simple idea is going to unlock everything for us. Let's kick things off with the most basic and honestly, the most important pattern in computational thinking. It's called the iterator. Don't let the fancy name fool you. It's just a formal word for a simple, repetitive loop. So here's our very first puzzle. You've got your stack of cards. How do you go through every single one and, this is key, guarantee you see each one exactly once? No skipping any and no counting the same one twice. It sounds almost trivially simple, right? But creating a foolproof process for this is step number one. And here is the beautifully simple solution, the iterator pattern. You start with your whole stack in an unseen pile. You pick one card up, you look at it, and then, here's the secret sauce, you move it to a new pile, a seen pile. You just keep doing that until the unseen pile is totally empty. And voila, you've just created a process that absolutely guarantees you've handled every single card perfectly. And this quote really gets to the heart of why this matters so much. A computer is a master at repetitive tasks. It'll do the same thing a billion times without ever getting tired. But us, humans, we get bored, our minds wander, and we make mistakes. By defining a clear, simple pattern like this one, we design a process that can be executed flawlessly, whether it's by a person or a machine. Okay, awesome. So we can now loop through every card without messing up. But just looking at them isn't all that useful, is it? We need some tools to actually do something with the information we're seeing. Think about it. As you're going through that stack of student grade reports, how do you remember what you found? If you're trying to add up the total marks for the whole class, you can't possibly hold all those numbers in your head. You need a place to keep a running tally. And that, my friends, is the job of a variable. It sounds technical, but just think of it as a separate notepad sitting next to you. It's just a named place. You could call it total marks, where you can store a piece of information that you're going to update as you go. Now look at how this one tiny change completely transforms our process. On the left, we're just kind of looking at cards, window shopping. But on the right, by adding one simple step, updating our total on the notepad, we've turned passive observation into active calculation. The variable, in essence, gives our loop a memory. All right, our little system is getting way more powerful. But what if the task gets more specific? Like, what if your boss asks for the total marks for only the female students? We can't just add every card to our total anymore. We need a way to be selective. This brings us to our next tool, filtering. And it's really just about asking a simple yes or no question for each card we pick up. For our example, the question is the gender on this card female? If the answer is yes, great. We add the marks to our total. If it's no, we just ignore it and move right on to the next card. It's like a little gatekeeper for our process. So let's take stock. We can iterate, we can remember things with variables, and we can be selective with filters. These are amazing tools for looking at one card at a time. But what happens when the problem requires us to compare cards to each other? Things get a little trickier. Let's tackle a classic problem. You have a class of 30 students. How do you figure out if any two of them share a birthday? Well, the most obvious way, right, is to pick the first student and compare their birthday to the other 29. Then you pick the second student and compare them to the remaining 28, and so on and so on. This is what you'd call a pairwise comparison. But that obvious method, for a pretty small class of just 30 students, it requires a jaw-dropping 435 individual comparisons. Can you imagine doing that by hand? It would take forever, it'd be super boring, and you'd almost certainly make a mistake. There has to be a smarter way. And of course, there is. This, right here, is where computational thinking has its aha moment. Instead of just plowing through with brute force, what if we could change the very structure of the problem to make it way, way easier to solve? This brilliant solution is a technique called binning. Instead of comparing every student to every other student, we do something clever first. We create 12 piles, or bins, one for each month of the year. We go through our stack just once and place each student's card into the correct month pile. And suddenly, the problem is transformed. We only have to check for matches within those tiny little piles. Those 435 comparisons, they shrink down to just a handful. It's a game changer. So, we've been sorting these imaginary cards this whole time, but why? Why does any of this actually matter in the real world? Let's zoom back out for a second. It matters because these simple, almost physical patterns we've talked about, they are the absolute bedrock of modern data science and software. Iterating through data, storing results in variables, filtering out what you don't need, restructuring it to solve a hard problem, that's how your social media feed works. It's how Netflix recommends a movie. It's how scientists analyze massive data sets. It's all these core ideas just running at an unbelievable scale. So, let's quickly recap our new mental toolkit. At the end of the day, computational thinking is all about finding those reusable patterns. Iteration is your tool for being systematic and thorough. Variables give your process a memory. Filtering lets you focus on only what's important. And restructuring your data, well, that's your secret weapon for turning really hard problems into much, much easier ones. And that brings us to the final thought I want to leave you with. What's a big, messy, complex problem in your own work or your life that might start to look a little bit simpler if you try to approach it with these tools, with steps and filters and patterns? Something to think about. Thanks so much for joining me.